results. Here is the nonlinear model without epoxy we just showed, and here is the model with epoxy, and we can see the stress results with less than 1% difference between the two models. And here shows the model that we did in AutoCAD. So what we do is that we bring this modified geometry with the retaining feature here, bring back AutoCAD, and would also adjust the adhesion factor here to simulate the kind of soft nonlinear contact, which is due to the epoxy. And we found by apply a scaling factor of 0.28, we get a similar result, stress results from AutoCAD to the nonlinear mechanical model. So with that, now we can move on to the next step to optimize to adjust the geometry retaining feature and epoxy shape and then reduce stress furthermore. In this study, we defined two parameters. One is the round here, and another round around the layer 2 bridge. And then we give a range of for the two parameters. And then we want to see is when we adjust the radius of these two features here, can we reduce the stress even more? In this simulation, we use the nonlinear contact model between the magnets and the laminations. In the first plot, we show the sensitivity study performed and show the result between the equivalent stress around the layer 1 magnet and the radius of that pocket. What we found is that with the increasing radius, the equivalent stress keeps going down. And we also see a similar trend between the round and the stress around the round at the layer 2 magnets. With the radius increasing, the stress goes down. We see some temporal fluctuation here. We suspect this is due to the numerical noise. And here shows the optimized model versus the baseline nonlinear model we see before. With the optimized model, with a basically larger radius of the round here, and here we see about 9% lower stress in the structurally optimized model. Next, we want to calculate the fatigue life based on the stress calculation. The first fatigue calculation is based on single loading step, basically loading from 0 RPM to 18,000 RPM. And what we showed here using fatigue tool within mechanical, we can choose a different type of loading type. We can choose a different type of mean stress theory, and then calculate fatigue life. In the example here, we calculate fatigue life to be more than 9 millicycles, and it satisfies the specification for the optimized design. Next, we want to do another fatigue calculation, which including preloading step. In the preloading step here, what we try to do is including the shaft interference load. We applied a 0.02 millimeter interference between the shaft and the rotor lamination, and that's the first preloading step. The second loading step is similarly applied with 18,000 RPM rotation velocity. So with the two loading steps included, we can use the solution combination feature in ANSYS Mechanical, and we give a scale factor and look at the stress in two loading steps. And in the example here, we use some solution combination, but if you have more than two load steps, for example, some customers want to include thermal loading history. In that case, Design Knife for Mechanical, which is add-on in ANSYS Mechanical using Encode Design Knife, that can include more than two loading steps. For the two loading steps here, solution combination works just fine, and use solution combination and fatigue tool in mechanical, we can calculate, again, based on the two loading steps, we can calculate the fatigue life based on different mean stress theory. Here's Goodman's theory is used here. And again, we can calculate fatigue life based on the two loading steps. And we found the minimum fatigue life is about 8.5 milliseconds here, and again, it satisfies the design specifications. So with the structurally optimized model finish, we can hand back the geometry to the final multi-physics analysis. Jonathan, please go ahead.
Cool. Thank you very much, Henry. So we've seen sort of before how we could sort of calibrate the adhesion factor and sort of take that learnings back into the analysis in Motorcad. So just to show that in a little bit more detailed, so we took the kind of customized geometry, the Ansys Discovery, export that as a DXF. Here we've kind of in order to kind of make the use of symmetry, we've kind of condensed that down into a single pole and a single slot. And then a case of just importing that DXF into Motorcad and setting a custom geometry. So with that in mind, so with that process done, what we'd like to do is then run it through the same multi-physics optimization workflow that we saw in the second webinar in the series. And then sort of retest the kind of the customized geometry through all the requirements that we have in mind. This is a relatively easy thing to do. We can actually make use of the Motorcad to Optiline export that we used in that webinar and the Python script that we generated. In the case of just pointing it to this new file and clicking run, and we can gather that information quite quickly. So here we are. We can sort of bring that all back together. So we have on the kind of like on the table on the right, we have the different requirements and objectives, the template design which came from the optimization, and then the resulting information sort of analysis when we run the same one, because it's kind of customized geometry that's been altered to kind of maximize the mechanical performance. So overall, we can see that we have a sort of very similar behavior in sort of some cases. So we have a kind of a very small drop in kind of the peak torque, which then kind of affects some of the peak power. However, most of the requirements that we had are kind of very similar within range. However, there's a couple of areas where we've just gone over the requirements, which themselves were quite harsh, quite sort of stringent targets, but they're very close to the requirements. So we've kind of called those as orange. So yes, we can see a little bit drop in peak torque and power, but still meets specification. Slightly higher losses, likely on the rotor, so that's sort of changing the thermal behavior a little bit. A little small increase in noise vibration harshness, but probably the biggest difference probably comes down to sort of the demagnetization resilience. So we have a bit of a degradation. However, overall, moving from this kind of template geometry and then customizing it for mechanical, we have a very good starting design from that point. Adding in these advanced features has made a small change, but overall we're very close to a final solution. And with a kind of another iteration, we could have sort of bring these requirements back into specification. And perhaps to sort of one to kind of look a bit closer, which may be an interesting one from a sort of mechanical design point of view. So this is the demagnetization at short circuit condition. So this is the kind of worst case scenario, which can cause permanent demagnetization. So we saw that it is a little bit worse with this kind of customized geometry. So in this particular condition, we want the flux to completely avoid the magnets to kind of go around into the posts and bridges, the same posts and bridges which are also being used for the mechanical strength. So they have quite a dual function, multi-physics function. And so we can see with a narrowing of the kind of retaining feature, that magnetic flux is traveling a little bit closer to the magnet, and that's causing a sort of a new area of demagnetization to occur. So with that in mind, with that knowledge, we can kind of go back to the parameterization. We could have a look at sort of perhaps changing the geometry of that retaining feature, adding in the height as a new parameter, and then kind of repeat this analysis and get a sort of an overall a better design that meets all of the multi-physics requirements that we have for the electric motor. Brilliant. So thank you very much. So just to kind of summarize, so the anterior pivot magnet rotor from the optimization workflow in session 2 was taken. It's exported to ANSYS Discovery and then into ANSYS Mechanical. Modifications were made to include magnet retaining features to kind of more accurately represent a real-world machine, and that was using sort of geometry parameterization on top of the existing geometry. With that in mind, we could conduct a detailed mechanical analysis, including the use of nonlinear contacts, additional boundary conditions, and lifetime fatigue analysis to give a more of a more detailed look at the kind of these aspects of the rotor of the electric machine. Then to kind of complete the cycle, that customized geometry was brought back into MotorCAD. We learned from that analysis, and we were able to kind of replicate a more representative analysis in the mechanical analysis in MotorCAD, but also conduct a multi-physics analysis and see how the new geometry behaves in terms of meeting all requirements. Excellent. Thank you very much. So just to kind of sort of run out the presentation today. So please do make sure to head on to the kind of additional training at the ANSYS Learning Hub. There's sort of additional classes you can join. Lots of different areas such as MotorCAD, ANSYS Mechanical, and other topics that sort of meet the other webinars within the series that we've observed so far. And also, so please stay tuned for additional webinars to come. So next on the list is looking at noise, vibration, harshness in electric machines and electric drive systems.